Hi, everyone. So we're going to start it again. Thank you, Josh. Okay, so hope you had a good lunch, and we have a few more speakers for the day. So next up is going to be Alison Gopnik, who will tell us about a new theory, is what I heard.
a new, somewhat half-baked idea, which has been getting slightly more baked over the last couple of months. But this is a new set of ideas that I would really, really like to get feedback and help with. Okay, so I am a developmental psychologist, and why would people in AI be interested in what I do, and vice versa? And going all the way back to the very, very first Turing paper about the Turing test, Turing pointed out that, in fact, instead of trying to simulate an adult mind, we might do better by trying to simulate the child's. And for many, many years, everybody read the paper up to that point, and then they said, oh, children, forget about it, and they ignored it. But over the past little while, with the increases in machine learning and the new AI spring, people have increasingly gotten interested in the idea that we could actually learn something important by looking at children, because of course children are the best learners that we know of. So when we're looking at adults, we're looking at a program that's already been determined, whereas what we'd really like to know is how you could construct a program like that from experience. So this is my sort of general slogan. What are some of the things that thinking about children and what we know about children's learning and development can tell us about how we should think about learning in AI? So one of the first things that I'm not going to go into in too much detail, but that I think is an important lesson that we learn, is that there's no such thing as general intelligence, whether you're thinking about natural or artificial intelligence. I should say, when I have given this talk a couple of times at computer science conferences, there's like a sharp intake of breath when you say this. It's like, what? Heresy! Don't tell the VCs, right? Why do I say that there's no such thing as general intelligence? I think the picture that comes from Cogsci, apart from a few little weird corners of psychometrics, is that instead what you've got is a lot of different, not only are there multiple intelligences, but those intelligences actually trade off against one another. So you have different kinds of cognitive capacities with different objectives, with different computational character, with different biological bases, and they actually often push against one another, so that being really good at optimizing one will actually make you worse at optimizing another. And I think there are a lot of these. This is the paper, by the way, where we argue for this, and we have some empirical data about it. But the three that I'm going to talk about particularly are a very old example of this contrast, which is the contrast between exploitation and exploration. The idea is that one thing you could be trying to do is maximize utility. But another thing that you could be trying to do is just get as accurate a picture of the world as you can, maximize your true information about the world as you go through the environment. And of course, in reinforcement learning, there's an optimization theory. There's classic results about the fact that you can't maximize both of these things at the same time, and trying to figure out how to balance them is a really important problem. But it's not just true in reinforcement learning. It's true in any situation in which you're trying to search a high-dimensional space of potential hypotheses or policies. You're always going to have this problem about how much should I be trying to extract information about the environment, and how much should I be trying to do the thing that will give me immediate utility. But there's a third kind of cognitive capacity, which is particularly relevant for humans, which is this capacity to get information from other agents. So I think of this as being transmission. This is the basis of culture. It's our ability to actually not think through either exploitation or exploration, just find the thing that the other people around you are doing, or the thing that the other people around you have discovered, and internalize it yourself. And if you think that maximizing utility is sort of the objective function for exploitation, and maximizing truth is the objective function for exploration, maximizing the convergence between what's inside your head and what's inside the heads of the other people around you is sort of the objective function for this kind of cultural transmission. And something I'm going to talk about in a month from now at the next session, but I'm just going to mention now, is I think one of the confusions about large language models is thinking about them as if they were agents that were trying to do exploitation and exploration. In fact, they're mechanisms for transmission. What they do very effectively and in a very interesting way is take all the information that human beings have accumulated over the past centuries and designed a novel way of getting that information to be available to other human beings. They give you a new way of extracting information that other people have accumulated in the past. And in that sense, I've argued they're cultural technologies. They're like writing or language or print. They're ways that you can actually extract information from others rather than being systems that are actually going out and exploring and trying to maximize the truth about the world. And that's the reason why they do things like have hallucinations. But what I'm going to do today is not talk more about that, except to say what I want to focus on today is this second capacity, which is the capacity to actually go out to a novel world that you haven't seen before, that nobody else has seen before, where your grandmother and the internet is not actually going to tell you what the right answer is, and figure out something about how that environment works and use it to act further on. And the particular kind of exploratory epistemic cognitive capacity is one that I've been studying for the past 20 years, is learning about the causal structure of a new environment. And for obvious reasons, although that's not the only kind of environmental structure you could learn about, it's a really important and useful kind of structure to learn about. And of course, that's the basic thing that we do in science, is figure out new facts about the causal structure of the world. That's what science is all about. But over the past 30 or 40 years, we've discovered that even very little children are developing intuitive theories of the world in much the way that scientists are. And one of the things that they are very motivated to do is extract the causal structure of the environment around them. And you can see why finding it, well, I'll talk about this a little bit more later on, but finding causal structure is incredibly useful and important because it lets you act on the world in effective ways, even more than, say, finding out about, say, the spatial or geometric structure of your environment. So this is a very good example of something that is a really useful exploratory cognitive capacity. And it actually lets you learn about novel systems. So over the past 20 years or so, in my work and other people's work, and particularly work in philosophy of science and in computer science, there's been a lot of progress in terms of giving a formal account of how causal learning and causal knowledge are possible. Probably the work that people here would know most about is Judea Pearl's work about causality. And essentially the idea is that you can represent causal information, causal knowledge, formally as directed in terms of directed acyclic graphs that have specific relationships to conditional probabilities. I'll get back to that in a moment. And that enables you to actually have a formal model of causal structure, use causal structure for inference, learn causal structure from data. What's the idea of causation that underpins this approach? What does it mean to say that something is a causal relation as opposed to another kind of relation? The idea that comes out of the philosophy and computer science and philosophy of science is that you should think about causation in terms of intervention. This is not the only way you could think about causation, but this is the idea that underpins the causal Bayes net approach. So variable X causes variable Y if and only if an ideal intervention on X changes the value of Y. So this is why randomized control trials are the gold standard for doing causal inference in science, why if we actually want to figure out whether there's really a causal relation there, the ideal way we do it is we do an ideal experiment, we go in and vary X, and then we see what the effect is on Y. The way that I like to think about this in terms of technical terms is that wiggling X will make Y wiggle. And in fact, that's Jim Woodward's technical philosophical term to describe this interventionist account. Now, there's a lot of details about what counts as an ideal intervention in the philosophy of science and computer literature. I can talk about this a little bit later on. And in fact, in science, for example, with something like a natural experiment, you could say that something was an ideal intervention, even if it wasn't an actual intervention that people produced. But freely willed intentional actions are a very good proxy for interventions. So if you think about it, a human agent that's going out and doing something to the system at a particular moment intentionally to figure out how the system works, not themselves influenced by other variables in the system, and then observes what the outcome is, that's a very good proxy for an ideal intervention. And that's a point that I'll get back to in a minute. Okay. So it turns out that with this, and the beautiful thing about the formalism is it gives you a way of not only talking about predictions among variables, but it also gives you a way very specifically and formally of saying, if this is the causal structure, here's what we'll be able to predict about the value of one variable from another. But here also is what we'll be able to say about the consequences of interventions. And another thing, we have Toby here, but so I won't talk about it, I'll leave it to Toby, is that it also tells you about counterfactual inferences as well as actual inferences. And that makes it different from a kind of classical associationist model, like a kind of classical neural net, for example, where you can predict the value of some variables from other variables, but you don't have this kind of asymmetry about interventions and counterfactuals. And the interventions and counterfactuals are what makes this a causal relationship. And it turns out that from a computational perspective, these causal models can actually give you computational accounts of causal inference. You can say, here's what the causal structure is. If this is the causal structure, here's what the statistical pattern among the variables will be. And therefore, at least in principle, you can use a kind of Bayesian inference and say, okay, now if I have this pattern of data, correlations and predictions, and interventions and counterfactuals, this is the graph that was most likely to have generated that data with good old-fashioned Bayesian inference. And perhaps most strikingly, from my perspective, it turns out that if you look at very little kids, it looks as if they're acting beautifully in concordance with this formalism. So we just did a review in Nature Review Psychology, looking at the development of causation in general. And 4-year-olds can do all of these things. So 4-year-olds can infer complex causal structure. They can find unobserved variables. They can infer theories in ways that that match the formalism. How could we test this? How could we say that this is true? We don't actually do anything foolish like ask kids to make judgments about probability. What we do is we give them a little toy. You saw in the previous picture, our Blicket detector, a little machine that lights up and plays music when you put some things on it and not others. We give them the little toy. We give them a bunch of data about that toy, which of course we control. Here's what the statistical dependencies are between different patterns of blocks and different outcomes. And then we just say to the kids, make it go. And so we've given them the data, and then they have to make the inference about the causal structure. And the gold standard for whether they made that inference correctly is, can they figure out a novel way to actually make the machine work? Okay. Now, one interesting thing about this this approach is that it turns out that children can do it to learn novel causal structure. So not only do they have a lot of causal information to begin with, this speaks to some of the things that that Shimon Oman was talking about yesterday, but they can actually use this from a very early age to discover causal structure that isn't part of any kind of evolved background. So if you have a 1-year-old, you'll know that remote controls are favorite toys of every 1-year-old, and you have to watch out that you don't, all the remote controls in your living room don't disappear if you let your 1-year-old crawl around the living room. And that's a nice example of something that doesn't seem to be part of our innate ideas about how causality works, but that babies are very interested in and learn very quickly. And there's a number of beautiful empirical accounts that show the way that children are using just their everyday exploration and play to try and solve causal problems. But there isn't any very good formal account of how that works. So how is it that you can decide, here's the experiment I want to perform, here's the data I need in order to be able to learn a novel causal structure? So what we've done in our experiments is we give the children a particular pattern of data, and then we say, here's 2 hypotheses you could have about how the system works. Which one do you think is the right one? But until this experiment I'm just about to tell you about, we haven't seen, will children just discover this in their everyday play and exploration? And we don't have good computational accounts of this. Okay, so now let me very briefly, I won't go into all the details of this experiment. One of the nice things about having about having online environments, and also a nice thing about having a generation of 3-year-olds who think it's perfectly reasonable to interact with online environments. This may be the most striking finding of all of this research, is that 20 years ago, we actually had to build the Blicket detectors because the kids wouldn't do anything on a screen. And now you put a 2-year-old in front of a touch screen and they're perfectly happy to treat it like a causal system. And that also has the advantage that we can record what their exploration looks like. So in this experiment, what we did was looked at a particular kind of causal learning that's especially impressive, which is learning not just specific causal relations, like this Blicket will make the detector go, but inferring some of these abstract hierarchical over hypotheses about the nature of the system. So for example, is this a deterministic machine or is this an indeterministic machine? Or in the case that I'm going to talk about, does this machine work with a disjunctive logic where either something's a Blicket or not, and if it's a Blicket, it makes it go? Or does it work with a conjunctive logic where you need combinations of things in order to be able to make it go? So you need a red one and a blue one together to be a Blicket and to make the machine go. So the question was, could kids not only infer some of these low-level specific causal relations, but could they infer these abstract hierarchical principles about how causal relations work? And in previous work, what we discovered was that not only can they do this, but they're better at it than grown-ups are. So grown-ups take their prior assumptions, their prior inductions about what causal structure is like, and they just apply it independent of the data that they observe. Whereas children will actually use the data they observe to try and figure out what the more abstract structure of the causal system is like. So what we did in this experiment was we simply gave the children these machines that had different kinds of causal structure, and we did it with this virtual Blicket detector. And we just, here's a picture of it. It's interesting also that we started out doing this virtually, partly because it was during COVID and we couldn't actually test kids in the lab. Here's a child who's using this interface to play with a virtual Blicket detector. And we just said to them, I want you to just play with this and figure out how it works. And then after 4 minutes, we said, okay, now tell me, what should I do to make it go? Which ones are Blickets? So we just let the children explore themselves. And again, I won't go into all the details, but the children were very happy to do this. They typically produced between 20 and 30 different trials. And a majority of the children actually produced all the evidence they would need to disambiguate the abstract causal structures. Sometimes the kids got the hypotheses. We said either it works with each Blicket separately or it works where you have to have a combination. Half of the kids didn't even have any information about what the hypothesis space was like. And nevertheless, a majority produced all the information you would need to disambiguate. And most of the kids produced, as you'll see in a minute, most of the kids produced enough information to get a reasonable hypothesis about how the system worked. And the children succeeded. So the children chose Blickets correctly, and they come out differently in the two cases of the different kind of causal structure. And then when it came to actually acting on the machine, which is, as I say, is sort of the gold standard, if they had seen a machine that worked conjunctively, they were much more likely to say that you needed 2 objects to put it on, whereas if they had seen a machine that worked disjunctively, they said that it was 1 object. And again, these are new objects, not ones that they've actually tested. So the kids are very good at extracting the structure of this causal system just from experimenting. Yeah.
Like somebody you would pick out of the DMV line. What
Right.
do you do?
Well, it's interesting because we've done this with undergrads and people from the DMV line. And what they do is they have a very strong bias towards the disjunctive case. So even when you give them the data that shows that it's conjunctive, they assume that it's the individual objects. And we've done a gazillion prompting studies and other kinds of things to see if we could get them to do it. And so far, we've completely, with a poor graduate student of mine, like that was her dissertation, was we're going to figure out how to get adults to be better at doing this, and nothing that we did made any difference to the adults. Interestingly, we have a little bit of evidence that Amazonian hunter-forager adults are actually doing better at this, which may be because they're more used to thinking about these kind of conjunctive global causal systems rather than thinking about individual causes, or it may just be because they have a lot of ayahuasca. I don't know which of those is the right outcome. But for weird adults, all the weird adults are really, really bad at doing this, and I can talk some more about that later. They're fine in the disjunctive case, but they are very bad at learning the unlikely structure. Okay. But now, one question you could ask is whether other kinds of computational systems can do this. Let me put in a caveat right away. As any of you who have tried to compare humans to large language models will know, there's a sort of whack-a-mole phenomenon, which is that as you put up your data about the thing that the large language model can't do, somebody in the back on their laptop is doing prompting and giving RLHF so that now the next time the system is going to be able to do it. Or even just we found the next iteration of the system goes and reads your paper and takes out the information from the paper about what the right answer to the... This is not a joke. This is actually something that has happened to us with the large models. But at least the GPT-3 models were very bad at doing this. And there's a lot of other evidence from other studies that large models, as you kind of might expect on this transmission view, they're very good at encapsulating causal hypotheses that are already out there. So if you ask them what will happen if you drop a glass, they'll tell you that the glass will break. But what this task requires is you actually infer a novel causal structure that isn't a causal structure that's been around before. There haven't been any Blicket detectors. People haven't thought about Blicket machines, which is, of course, the reason why we use these kinds of systems when we're testing the kids. And there's other evidence that LLMs seem to be particularly bad at doing this kind of novel causal inference. And if you use an RL method, you can get them to do it, but no surprise, it takes 720,000 trials as opposed to the 20 to 30 trials that the kids are using. And note that this is true even when we do a symbolic. This is not because they have to learn from pixels. This is with a symbolic representation that says, here's the machine, here's the block, it's red or it's blue, and it's still really challenging to do from an RL perspective. And in fact, when they do solve it, it looks as if what they do is overfit. They just try every conceivable combination and look at all the conceivable outcomes, and then they just make that the inference based on it. Okay, so what is it that, in fact, that the kids are doing that's enabling them to do this so effectively? And the idea that we've had, and that comes from a whole line of research in cognitive science, that sort of Bayesian approach to cognitive science, is that they're doing some kind of Bayesian hypothesis testing. They've got a range of hypotheses about causal structure. They're trying out one of these hypotheses. They're checking it against the data, and they're choosing the hypothesis with the highest posterior. Which would be nice, except that we know that that involves these terrible intractable search problems. And I have to say, like for 20 years, I kept thinking, well, we just keep working at it, we'll solve it. We'll solve that problem. And we didn't even make very much progress on trying to solve that problem. So there's kind of I think we're at a kind of impasse with this approach to trying to solve causal learning. Okay, is there any other thing that we could do that would help us with this impasse, given that the kids are doing it? And an idea that everyone knows about here is that's come out of the AI literature is instead using reinforcement learning. And reinforcement learning is indeed a method of figuring out something about novel structure in the world. I have to say that as a boomer cognitive scientist, the first time that I heard AI people talking about reinforcement learning, my reaction was, oh my God, no, we're going to have to go through this again. Are we going to have to wear bell bottoms next? Is that going to be the next iteration of this? But of course, it's interesting that for a long time, people have noticed that reinforcement learning you could think of as being a very primitive kind of causal learning, because reinforcement learning has the same interventionist structure that causal learning does, right? As opposed to, say, just various kinds of associative learning, including like deep neural learning. Because what reinforcement learning is about I take an action on the world, and then I observe what the outcome of that action is, and then I change my policies and change my world model as a result of that. So it has a very causal, it has a kind of causal flavor, but of course, it is not really like the kind of causal learning that I was just describing, because it's motivated by utility, right? The thing that shapes it isn't about, have I epistemically figured out the right structure in the world. It's have I gotten more reward than I would have done otherwise. So it's not like the kids sitting there trying to figure out the machine where they're just going out and doing, or scientists just going and doing a bunch of experiments. It's like, it's all broader impacts in RL, you know, it's all, here's why this is going to actually help the world at the end, as opposed to that being just the boilerplate you put on in the end so that you can get your grant, right? And of course, we know that it doesn't work as well in high dimensional open-ended kinds of environments, the kind of environments that humans are learning about. And as I said at the beginning, it faces these explore-exploit trade-offs that are very difficult and challenging. On the other hand, the kind of Bayesian causal learning that I was talking about is epistemically motivated, and it allows structured hypotheses. It gives you very good generalization. But as I said, it has difficulty with exploration, and it faces these intractable search problems. So the question is there something that you could do that would bridge causal learning and reinforcement learning in a way that could give you some of the advantages of both? And the new idea that I want to argue for is that you can actually find an interesting candidate for this kind of bridge in the literature about intrinsic epistemic rewards in reinforcement learning. So there's been a bunch of work trying to show that if you take a reinforcement learning system and instead of just giving it a reward of utility, how much juice have you got, how much positive reward have you gotten, you actually give it an epistemic reward. Like now you're being rewarded for finding something that's novel. And the classic example is information gain. So you actually reward the system for information gain, and you can get a system that looks as if it's more epistemic and does a better job of exploration than the kind of classical RL systems. But these information gain, curiosity, novelty kind of systems have the problem that they explore too broadly. So the classic failure mode is this: you put it in front of a TV with random static, and you're getting lots and lots of information, you're getting lots of novelty, but it's just not information that's relevant to anything that you want to do. And even if you don't have the specific problem about randomness, even just, you know, if you're looking around the room, all sorts of things in this room are novel, or things I haven't seen before, or things that are surprising. How do I know which things I should actually be trying to find out about, right? And the idea that people have been using recently, it's actually quite an old idea, and interestingly, it comes out of the eLife kind of background. This is this original Cuban paper in 2005, but people have been trying to use it more recently in actual RL, is something called empowerment. So empowerment is the idea that what your reward is to maximize the mutual information between the variability in your actions and outcomes at the same time that you maximize the diversity of actions. And really, a way of thinking about it is its controllability becomes the intrinsic reward. So it's not novelty or randomness, it's how good am I at being able to control my environment? How I'm going to seek out things in my environment such that I can actually make a difference to them. And variation in my actions can make a difference to variations in those outcomes. And independently of whether there's actually any intrinsic reward to those outcomes, I'm going to think it's good for me to find ones that I can control. And you can see how this works. What that means is that in the long run, it's a bit like with meta-reinforcement learning. In the long run, you're going to have a repertoire of things that you can actually do out in the world if you are now facing a novel problem in a new environment. And it rewards exploration and discovery. And the crucial claim that I want to make is that empowerment, and particularly empowerment gain, I've had various strengths of this claim, but at least one version of this claim is that it necessarily is going to lead you to gain causal knowledge and vice versa. In fact, I think you could almost make the case that it is causal, what we mean by causal learning. Because think back to that interventionist account of causation that I mentioned. The interventionist account of causation, right, is that it's a causal relation if I wiggle X and I get an effect in Y. And what empowerment says is look for things such that if you wiggle X, you'll get Y to wiggle. Find those out in your environment and perform actions that will enable you to do that. And I think that it follows necessarily that as you get more and more empowerment, we can talk about this a little bit later on, that's going to lead you to gain more causal knowledge. So as you go, and again, think about science, right? You do the experiment, you find out what kinds of things you can actually bring about, and now you can design the rocket that will take you to the moon. And vice versa, even if you're gaining causal knowledge through an indirect route, not necessarily through the experiments themselves, maybe somebody tells you, oh, the moon is responsible for the changes in the tides, even though that's a pretty indirect causal claim, what you can conclude from that is, and you know what, that means that if I could move the moon, the consequence would be that the tides would change. So I think there's a very intimate connection between these two. And I was thinking with the talk yesterday, there's something you could think of as sort of scientific pareidolia, which is that when you get a good idea, you start seeing it around you everywhere. But I do think that in this case, if you actually just look at babies, one of the wonderful things about being a grandmother in 2024 is that you get a stream of videos of your grandchildren every morning. So these are random videos of my grandchildren. What you'll see is behavior that looks, let me turn this up a little bit. What you'll see, this is a 9-month-old. What you'll see is behavior that actually looks much better characterized by an empowerment reward than it certainly does by a utility reward. So what you can see is she's sitting there bouncing this thing and looking at the various kinds of outcomes that she gets from bouncing it, including tasting it. And now she's going to taste it again from a different angle. And then she explores it some more. And now she's bouncing it. And notice that each variation in action is actually leading to a different outcome with this kind of physically kind of weird object. And then she takes the block and bounces it, knocks it some more. Let me give you another example from another grandchild. This is actually Kit, who some of you may remember as my co-recipient of the Rummelhart Prize. And you can see Kit's got the xylophone, and one thing that he does is use the mallet to actually make noise. Then he tries it with the other end, the stick instead of the mallet. Even though the mallet's actually, if you were doing classic reinforcement learning, he's done a perfectly good convergence on a good method for getting that noise. And then he takes his hand and decides that he's going to try it to see if the variation in his hand is making a difference in the variation in the sound. And he tries it at different kinds of angles. He tries it at different places. He tries it with different kinds of hands. And there's another interesting thing about this video in particular, which is that he's doing this as his grandfather is playing the piano. His grandfather's a musician, and his grandfather is making beautiful music on the piano. And I think, I'm not sure, but it looks as if part of what's going on here is that Kit is seeing that there's this causal relation that's out there that another human being is implementing of doing things with your hands such that you get a complicated auditory result, and then he's implementing that himself. Yeah. Exactly. So the thought is that empowerment is a subcategory of exploration. So the idea is that exploration itself is this very wide-ranging thing that you could be doing, and empowerment is the specific subset of exploration where you're exploring the consequences of variability on your own actions on variability and outcomes in the world. And one of the things that we know is that from the time they're very, very young, babies are interpreting the actions of other people as if they were like their own actions. So they're using the actions and outcomes that the actions that they see other people perform and the outcomes of those actions as if they were proxies for their own actions and outcomes. Yeah? Sorry? Oh, okay, good. There we go. Good question, and I'll get to that in a second. And it turns out that actually there's a psychological literature about this, and it's got a very interesting history. Back in the 70s, when reinforcement learning and bell-bottoms had their first period of enthusiasm, Carolyn Roby Collier wanted to see, could infants be operantly conditioned? And she set up this very nice apparatus where the baby's foot is attached to a mobile, and then she just watched what the babies did. And what she discovered was, first of all, nicely, the babies immediately start kicking in a way that will allow them to activate the mobile. But I mean, it's wonderful to read her paper about this. She says, but this is kind of strange. It doesn't look as if they really want the reward of the mobile moving. Because if I move the mobile, they won't even look at it. They'll just give it a glance. And they keep stopping halfway through and looking to see what happens if they don't kick, and then seeing what the outcome is. And they coo and they laugh, and they're really, really happy about being in this situation with a ribbon. And there's been work since then that's shown that, for instance, the babies are systematically altering their actions in this kind of a setup and then observing what the consequences are. So it looks, and she says, it looks like the contingency is actually the thing that's the reward for the babies, not the outcome, not the reward itself. And I was talking to Amanda about whether there's examples of this in non-human animals as well. So we have this information about contingency learning in infancy, and there were a whole series of these experiments in the late 60s and early 70s. And we have some similar kinds of findings with preschoolers more recently in the context of this causal learning work. So you see the preschoolers as well are trying out lots of different kinds of actions too, and looking at their outcomes in their everyday kind of play. And we actually have an experimental result about the relationship between this and causal learning that I think is very relevant and interesting, which we just kind of did, and it was a weird thing, and we just left it there for 10 years. Two different groups did this experiment back in 2010. And what we discovered was that if you do look at toddlers, initially, toddlers will only infer causal relations if they're the outcome of human agency. And interestingly, for toddlers, I think as opposed to non-human animals, it doesn't matter whether it's the other person's agency or your own agency, but it has to be a human who's actually doing something. And here's the way the experiment goes. You have this little puck, and it hits one or the other of these blocks. And when it does that, that egg lights up. And the kids are interested in the egg lighting. So the kids see in one condition, the experimenter moves it in one direction and it hits this block, and then the egg lights up. In the other condition, it just moves by itself and it hits the block and the egg lights up. Then we just look at what the babies do. When the babies see it hit the block by itself, even before the egg lights up, in both conditions, they look towards the egg, which means that they've done the prediction. They've done a nice association prediction that when this goes over here, then the egg will light up. But if you ask the babies, make the egg light up, these are toddlers, they'll do it if it was the result of the human action, but they won't do it if it was just the result of the object moving. And we did a bunch of controls to show that they can do it and they're not put off by it, et cetera, et cetera. And as I say, we found this in a number of different experiments. 4-year-olds, on the other hand, will do this whether it's the result of human agency or not. So 4-year-olds will do it even if you just see the puck move by itself. And what we argue in this Nature Reviews paper, which some philosophers have argued as well, is you could think about it as being a kind of 3-step process for understanding causation that starts out with this kind of first personal reinforcement learning account of causation, where you do something and then you see what the outcome is. And then it becomes this second personal one where you see another person, you see another agent do something and you see the outcome and you infer that there's a causal relation. And finally, you get to the point where you can just say the moon is causing the tides, even if there's never going to be an agent that's actually going to go in and wiggle the moon and see the tides. But in principle, if there was an agent that did do that, if we could do that, if we need to do that for the tides at some point, we could do it. And that discriminates, that makes causal relations different from other kinds. Last? Okay, great. So my plea now is the problem with thinking about empowerment as this reward is, surprise, surprise, it turns out it's intractable too, because basically everything except gradient descent is intractable. That's my learnings from hanging out with computer scientists for the past 10 years. So the question is, are there various kinds of approximations we could give that would allow us to think about using empowerment in artificial systems? And I'll just end. The thing that actually started this was work with, especially with Yuqing Du and Li Dian in computer science at Berkeley, where what we did was we started out just using this open-ended Minecraft crafter environment. And this is a nice example of an environment that requires a lot of exploration and that typical AI agents are bad at solving because they won't explore the space enough. And we put participants into this into this environment. Again, with the kids, we just said, just figure this out, have fun, play with the game. And we did this with both adults and children. And then we looked at the relationship between different kinds of measures of intrinsic reward. We looked at entropy, we looked at information gain, and we looked at empowerment and the degree of exploration that the agents, the children, performed. And we discovered that the more empowerment, the more you could characterize their actions as maximizing empowerment, the more they effectively explored the space that was available to them in the game. And what we're trying to do now is see if we actually trained an agent to maximize empowerment, would it end up solving some of these exploration problems that agents typically have trouble with? And as I say, the problem is we don't have enough GPUs to actually do that because it's like everything else, it's interactable. The very last thing that we're doing is we're actually looking at children's free play. So we have a database of just children just playing with play sets, just play and have fun. And we've been analyzing this data set in terms of measures of empowerment. And I think you can just sort of see intuitively that a lot of what the kids are doing when they're doing something like playing with a play set is trying variations on actions and then trying to see what the outcome consequences are of the things that they do. I think I will. Maybe I'll just briefly describe this experiment, and then that will be the end. I'll give my acknowledgements and funding. Speaking about the comparative case, can we see this in non-human animals? There's one really striking result that I love, one of my favorite results in all of psychology. Go back to operant conditioning, right? Reinforcement learning is all rooted in John Watson and operant conditioning. You put the rat in the maze, it goes down one arm, it gets a shock, it goes down the other arm, nothing happens. It will never go down the arm where it got the shock again. It will only go down the arm where nothing happens. And of course, that's a kind of classic explore-exploit trade-off, right? Because maybe it's a non-stationary environment. Maybe there's cheese in the shock arm the next time, and the animal's never going to find out because it's just trying to maximize utility. It turns out that is not true for juvenile rats. So if you look at juvenile rats, they prefer the arm that leads to the shock. And of course, if you're thinking about it from an empowerment perspective, even though your utilities are going down, your empowerment is going up. And if you think about like my 3-year-old grandson playing with a stick, right, the utilities of the stick play are as likely to be that you end up with grandma having to take you to the emergency room as that you end up, being able to reach a distant object. But the little kids especially are preferring the empowerment reward. But there's a last twist to this, which is that the juveniles will only do that if the mother is present. And Nib Tottenham recently replicated this with human 3-year-olds. So only if there's a caregiver present will they do it. But if the caregiver's been fear conditioned, then they won't do it then either. So if the mom is saying, don't play with the stick, you're going to end up in the hospital, right? Then they won't do the empowerment exploration. So what all this suggests to me is that it isn't just sort of coincidental that it's children who are engaging in this desire for empowerment, that the babies are the ones where you're seeing this. This is actually, I think, part of our life history design. So I think our life history design is that we get this early period where we have a lot of investment in caregiving. And what that does is it enables us to do high temperature exploration and seek empowerment. And then when we're adults, we could take that very, very wide range of potential actions that we've discovered, and we can put them to use to do all the things that we want to do especially in novel, non-stationary, out of distribution settings. Okay, so let me end there with my assorted colleagues. And again, what I would really love is if someone could tell me how to get a good approximation for empowerment. I will mention the point about the outcomes, but maybe let's see if there's some questions first.
Amanda, if you can start getting set up, I think that will speed things up. Okay, questions?
Yeah.
I have a question. So, of these things that you talked about, what sort of neurosciences there are out? Which sort of do you know mechanisms that sort of govern some of the?
Yeah, that's a really good question, and I will defer to the neuroscientists. One thing that is interesting from this life history perspective is we know that juveniles in general are doing this much more than adults. So juveniles are producing more variable, noisy, random behavior, and they're more engaged in looking at what the outcomes are. I don't know what the mechanisms are. It doesn't look like it's a kind of dopamine-driven exploration, but exactly what's driving it, I think, is kind of up for grabs.
You mentioned that this issue of finding actions that maximize empowerment is computationally hard to identify.
Right.
Could you explain how you think that toddlers are able to do it if it's computationally hard?
Yeah, that's great. That was exactly the point that I was going to make before. So there's two reasons why it's computationally hard. One of them is just divvying up the data. So if you're trying to do it at a pixel level, it's going to be really, really, really intractable, right? And then the other is, of course, trying to divvy up the action space. So knowing what counts as being the right action is really challenging. But I think in a way the toddlers get both of those things for free, because they get the action space because you have to represent the action space just to act, right? So you've already got the representation of the action space because it's the action space of all the stuff that you do when you get a stick, right? And I think in terms of the outcome space, to speak to the point before, the kind of intuitive physics, core knowledge, whatever you want to call it, that someone like Tomer would describe, at least as a first pass, or even just what the visual system gives you as a first pass. There's objects, they move, they're in contact with one another. There's agents. There's a difference between objects and agents. Agents are things that, move in a particular kind of way and treat the agents as if they were doing ideal causal interventions. I think a lot of that stuff is going to be given by your inductive biases. But I think it's interesting that the way and the third thing is, in like Carolyn's work, the temporal window between the action and the outcomes is quite short. So it's like seconds between the two. And it doesn't work if it's like 20 minutes later after you pull the ribbon, then you get the outcome. And another reason why it's intractable is if you're trying to calculate this over multiple time steps, then you can see why it very, very quickly is going to explode. So I think for the babies, this is one of those cases where the bugs are actually features where the fact that they've got a smaller time window and a smaller set of perceptual things that they're considering is actually really helping them to be able to solve this problem. But I think it would be very nice to know, if you do know what the actions are and you do have a more limited set of outcomes, can you solve the empowerment problem without its blowing up? One other thing to say about that, speaking about the core knowledge kind of ideas, I think it's important, though, that the way that people typically think about the effects of intuitive physics or core knowledge on these inference problems is they're constraints, right? So you're not going to consider all the hypotheses that violate your intuitive physics, and that's going to make the search space narrower. But the thing that I think is so interesting about this is that you can end up with causal relations that are completely unintuitive, that completely violate your intuitive physics, like, really that mobile and ribbon one from the baby's perspective is just mysterious, like what happened, so now I'm kicking my foot. And you can discover those causal relations, which of course is exactly the thing that science, for instance, lets you do. So having the core knowledge does give you an inductive bias that helps, but it's not helping because it's constraining the search space. And I should say my sort of vague intuitive picture of this is you could think about it as what this lets you do is find a bunch of causal arrows. It makes you find a bunch. If you think about the Bayes-Net kind of directed graph picture, what this does is say, go out in the world and just play and do all this stuff. Look, this one, the stick one, that's a really good causal arrow. And now I want to have a more complicated hypothesis about, here's an object that's out of reach. What can I do to get it? And I can use this causal relation that I discovered without having a bunch of hypotheses about sticks. I discovered just because I really love doing things that give me a high empowerment reward. And then I could combine those, put those together to actually have something that looks more like a causal hypothesis.
Okay, so I know there's a lot more questions, but let's save them for the break. So let's thank Alison again.